Hello. No, it's Monaco. And hey, we have a special guest.
Special guest today.
Wow. McCaffrey, what's good?
I'm here to transmutate your video.
Oh my gosh, you're going to turn us from one element into another?
Yeah.
One teacher into another.
But how would we show that on paper?
Yeah, we can do like how
cut. No, I'm just kidding.
Such as nomenclature.
Number 5. Video number 5.
Yep.
One more to go after this.
Absolutely.
Fresh videos. We make them. You watch them.
Here we go.
Law
of conservation of mass governs all natural radioactive transmutations. What is it, Mr. Milks?
It just means that basically everything we have on the left-hand side, we need to still have on the right-hand side. And in this case, we're not balancing equations before like we did before. We're talking about total mass, total nuclear charge.
Yeah. Now, I mentioned mass defect in a previous video showing that like matter can actually be converted into energy. We're not counting that matter that gets converted into energy here because it's literally fractions of the mass of a proton every time a transmutation occurs.
That's just need to know stuff so you guys
too
understand
small,
what's really
too
going
small.
on. But.
Well, we have to do some notation, parent nuclei and daughter nuclei.
Right. So the reactant nuclei on the left side of the arrow, remember, left side is always reactants.
Yep. So that's our parent. And the daughter is on the product side. So you're going to have your emission, like alpha, beta, positron, neutron, whatever, and some other nuclide. And that's called the daughter.
Right. What's left, right?
Yeah. And so the properties of transmutations are simple. Alpha decay. An alpha particle has a mass of 4 AMUs, a charge of positive 2. It is the nucleus of a helium atom stripped of all its electrons, traveling at extremely high energy, which is why we call it ionizing radiation.
Right.
And so the daughters, when an alpha decay occurs, are always 4 AMUs lighter and 2 protons fewer.
Right.
Simple enough. What do you got to say about beta, Milks?
Well, beta is an electron, so I got a no mass.
No mass.
And I got to charge it to -1.
Yep.
So it actually makes my charge go up on my daughter nuclei because it has to equal. So let's say I had a parent nuclei with 30 protons, and then I have this -1 charge on the product side. I actually need to have a 31 with that.
Like this example right here. Thorium becoming protactinium. 234.
He actually knows that that's protactinium. That's the kind of geek that he is, you know?
Wow.
I love that he knows that.
You got it.
No, you got it.
Oh, I wrote 234 here. This is actually the beta particle that I'm trying to draw.
Zero.
So 0 mass.
But it needs
E
a
is
minus.
the symbol, and -1 is the symbol.
There we go.
91 minus 1 is 90 that you started with.
Right.
So that's what we're kind of talking about there.
Oh, speaking of daughter nuclei, I gotta go get my daughters.
Go get your daughters.
I gotta take off, guys. But
See you later, McCaffrey.
kill it as usual.
There you go.
Positron. This is like the only time we mention positron this year. It's the opposite of an electron with charge. So it has no mass, just like an electron, but its charge is +1. So the daughter nuclei has the same mass as the parent, but it has 1 less proton than the parent does.
Right. So, and when I was doing the POGL today, there's actually another step to this that we left out for both of the positron and the beta. If I am changing my number of protons by 1 or by 1 in both cases, but my mass stays the same, my number of neutrons must also change so that my mass stays even.
Yeah, that happens very rarely, though.
Well, right,
In
but
positron
234 and 234, I'm changing my protons. My actual number of neutrons in the species that is my daughter is different. It has the same mass but different number of protons.
For sure.
So that's in the POGL where you have to be able to.
That's
do that.
like deep
deep, baby, deep.
Neutron capture is artificial type of transmutation. Neutron capture means your parent soaks up a neutron somewhere. And this is happening in nuclear reactors. It creates the nuclear fission reaction that we then control to produce electricity and heat and steam. That's what happens in a nuclear power plant. So they bombard uranium with neutrons and it causes it to decay to the fission reaction.
This is one of those need to know things that it's present. It won't be in any part of our practice.
Nope.
The other three will be part of our practice. And guess what's next?
Practice.
Here we go.
So let's, I'll grab a couple here.
Okay, so the first thing that I want to talk you guys through is the top number is the mass. And so if we're looking at number 6, this is the bottom half of your page, you see Bi has 209 and helium has 4. So I have a total mass of 213.
Yep.
And I have to have a total mass of 213 on the other side. And notice he wrote 212 already because he said, well, what number plus 1 equals that 213? 212.
This
All
is
right.
where you need a periodic table too.
Right, and you do need a periodic table. So now I got a nuclear charge of Bi has got 83 protons, helium has 2, so I have a total of 85. Neutron has 0, so I have 85 there. Then I use that number 85, not the 212. I use the 85 to figure out what atom is it? And is that astatine?
Astatine.
Astatine. Hey, I knew one.
There you go. Good job.
Okay. This next problem is going to go the opposite direction. Okay. My total mass on the right-hand side is 238 plus 2 because there's 2 neutrons, each one having a mass of 1. So I have a total of 240. It's got to be 240 on the left-hand side. He wrote a 1 down because 239 plus 1 is 240, right? And I have to have a total charge of 93. Boom, you see how we did it? We made it so the total charge on the left-hand side had a total charge of 93.
All right, let me try this next one. I bet you that's a 99 on top
Right, because I see a total of 99 on the left.
and a 43 on the bottom.
A 43 minus 1 is 42.
Which is what I see on the right. on
Look
the
up
left.
who is number 43.
It's next to molybdenum. TC, technetium.
TC, technetium.
Mm-hmm.
Okay.
TC.
These next two, we got to go from right to left. I see a total mass of 41, and I already have 1 on my neutron, so that's 40.
Mm-hmm.
And I have a total mass of 20, and I have nothing on my neutron, so I need 20. Who is atom number 20?
Calcium.
Ca, calcium. Beautiful.
Yep,
You guys
yep,
get the
yep.
hang for this yet? This is actually mad simple, and a few of my kids just having me direct instruction it finished all the practice without us even making the video.
Oh, yeah.
So
That's
Guess
the last one.
this is as complicated as these equations are really going to get.
Remember, the total mass on the reactant side has to equal the total mass on the product side. That's
Correct.
the top number, the larger of the
Yep.
two. And the total atomic charge, protons, on the
Right.
left side has to equal the total atomic charge, protons, on the right side.
Right, yeah, we actually call that nuclear charge. Remember
Nuclear.
from before?
Mhm.
Because they're the only, protons are the only subatomic particle in the nucleus with charge.
Right.
As a member of protons. And guess what?
That's it.
Yabba dabba dabba.
Transmutations.
See you.
That's all, folks.
One more and we're done.
Half-life coming right up.